Welcome back. Today we're going to make sure everyone can find the zeros of polynomial functions. Before we get started, let's review two theorems. The first is the fundamental theorem of algebra, which states that if you have a polynomial function with degree n, anything that's greater than 0, so like a line, a quadratic, a cubic, so on and so forth, you're going to have at least one zero in that complex number system. And remember, we're talking about imaginary numbers as well. So irrational, rational, real, and imaginary. Okay, the second theorem is the linear factorization theorem, and it also states that if you have a polynomial with a degree greater than 0, then you're going to have n number of linear factors for that function. So if we have a function here, x cubed plus 9x, well, we know we're going to have 3 linear factors. We're going to have 3 zeros. Okay, so to find the linear factors, you can just factor, and you guys know how to find the GCF. That's x times x squared plus 9. And at this point, when you're younger, you would have said, that's it, we're done. But now you know that x squared plus 9 makes 2 imaginary roots, right? So you would get x equals plus or minus 3i. Now, if you were going to put that back in there as a factor, you could set them equal to x, add or subtract them to set them equal to 0. Essentially, they're the zeros. So we would have f of x in linear factorization, okay, is going to be x times x minus 3i and x plus 3i. So when we ask for the linear factorization, we're looking for all 3 factors. Okay, now let's go over to x squared minus 16. So x squared minus 16, well, you know that's a difference of squares. So that factors into x squared minus 4, x squared plus 4. And you guys know this, and I'm not going to keep writing f of x here for a second. We know that this factors into another difference of squares, x plus 2, x minus 2, and years past, you would have left it just like that, right? But we know that we can factor x squared plus 4 into 2 imaginary roots, so that's going to be x plus 2, x minus 2, x plus 2i, and x minus 2i. And that's going to equal f of x. So whenever I give the linear factorization, I always make sure I write what is on the other side of the equal sign. Is it f of x, g of x, whatever we're talking about. Okay, so we knew that there was 4 factors because of that degree. Okay, now let's go on to the rational zero test. Now we're looking at possible rational zeros, not irrational. When we say irrational, remember we're looking at, that's square roots or non-terminating, non-repeating decimals. We're not talking about imaginary roots, anything with an I, right? So that's not included in the rational root test. The rational root test considers the factors of the constant, which we consider are p, and then the factors of the leading coefficient, which is q. Okay, so just make sure that whenever you're finding the p's and the q's, that you do have it in standard form. Your polynomials should be written in descending degree, right? So you can make sure we find those p's and q's accurately. Okay, so if we have something like this, x cubed minus 15x squared plus 75x minus 125, well, we know that we're going to have 3 zeros. Or we could say 3 linear factors. And if we want to list them, well, we have to look at the p's and q's. Remember, the q is the leading coefficients factors. So we don't have a number there, right? So that's 1. So it's going to be plus or minus 1. And then our our p will be factors of 125. So plus or minus 1, plus or minus 5, plus or minus 125. Well, you only have to divide everything by 1 because when we put P over Q, right, we're just going to have plus or minus 1 for that Q. So if we write those possible rational zeros, it's just going to be the same values as our Q, as our P. So plus or minus 1, plus or minus 5, and plus or minus 125. So those are going to be all the possible rational zeros. So we're not saying all of those are going to work, those are going to be the possible ones. So if we want to see if they actually work, well, we're going to have to do the work. Okay, we're going to have to plug those in. So we could try 1, and there's a couple ways you could do it, right? You could plug in 1 and see if you get 0, or you can use synthetic division. So this is 1, negative 15, 75, and negative 125. So when I bring down the 1, and I bring those over and add going down, that's definitely not going to be a factor, right? So we could plug that in and see that that wasn't a factor either. So let's try a different number. Let's try 5. So the coefficients 1, negative 15, 75, negative 125. All right, so bring that 1 down. We got a 5, negative 10 times 5 is negative 50. Add going down, and boom, there's a factor. Okay, so there's no remainder, so we know it's a factor. What you can do from here, you can write this as a binomial, or sorry, a quadratic, and we can factor it because it is a perfect square trinomial. So if we wanted to factor that, well, we know that that's going to be x minus 5 squared. So when we consider that function, f of x, we know that f of x, I'm just going to make a little line here to make it clear, is 3 of those x minus 5 factors. Okay, so if we wanted to find the zeros, well, the zeros is just 5, but it has a multiplicity of 3. Okay, so we know that cubic is going to go through 5, and that's going to be the one and only 0. Okay, let's look at a polynomial with a leading coefficient that is not 1. Okay, so here we have a quartic, so we're going to have 4 zeros. And when we consider the p's and the q's, so the q, again, remember, is the factors of 2, so plus or minus 1, plus or minus 2. And the factors of 30 will be our p, so plus or minus 1, this will be a little bit longer, 2, 3, all these are plus and minuses, 5, 6, I'll continue over here, 10, 15, and 30. All right, so we're going to have our hands full because there are a lot of possible rational zeros, because we're going to have to divide everything by 1, so essentially everything on that list for p, and divide them by 2, so that'll add some more. So p over q for all of our possible rational zeros, I'm just going to start with the largest, plus or minus 30, because when I divide that by 2, I get 15, which is the next one on the list. And when I divide 15 by 2, yeah, that's not on the list, right? So plus or minus 10, 5's on the list, so I'll come back to 5, 6, 3's on the list, 5, anything that's odd, I have to make sure I divide that by 2. Plus or minus 3, plus or minus 3 over 2, and the list continues down here, plus or minus 2, plus or minus 1, and plus or minus 1 over 2. Lots and lots of possible rational roots here. Okay, so for this one, we're going to try out some numbers. So let's try 2. Ooh, didn't mean to write that over there. Okay, so let's try out 2. And the coefficients are 2, negative 9, negative 18, 71, negative 30. All right, bring down the 2. We get 4, negative 5, negative 10, negative 28, negative 56, 15, and 30. That one's a winner. All right, let's try 5. So here we're going to bring down the 2 again. We get 2, 10, Add that going down, we get a 5. 5 times 5 is 25. -3, -15, again, a winner. Okay, so we know 2 and 5 work. We can keep going and keep plugging numbers in, but since I have a quadratic, we can also factor and see if that factors, right? So 2 factors, just do this little time. So the 2 times -3 is -6. I'm going to use some decomposition here. And -6, when I look at factors of -6 that add up to make 5, that's going to be 6 and -1. So I'm going to use decomposition here. So I'll make that 6x minus x minus 3. And we could just find the GCF for each of these. So x minus 3 is going to be the common factor, x plus 3. And so this will be 2x minus 1, x plus 3. All right, now before we get too far along, remember we did have those 2 factors from above. So if I was going to write this in linear factorization, f of x would be 2x minus 1, x plus 3. And don't forget those 2 factors that we divided earlier, x minus 2 and x minus 5. Remember, that was the factorization, but this is looking for the zeros. Okay, so we want to make sure we write those zeros out. So the zeros, there's going to be 4 unique zeros. So x equals 1/2, -3, +2, and 5. So those will be the zeros. And we also put in linear factorization, just for good measure. Okay, let's look at one more example. So here we have 4x cubed. Again, the degree is 3, so we're going to have 3 zeros, because that is the degree of the polynomial. When we consider the possible rational zeros, again, our q is going to be the factors of the leading coefficient. So that's plus or minus 1, plus or minus 2, plus or minus 4. Okay, and then our p will be the factors of our constant, which is 1. So p over q, all our possible rational zeros would be plus or minus 1, plus or minus 1/2, and plus or minus 1/4. Okay, so to plug those in, we could use synthetic division and see if any of those work, right? So if you want to plug one in, you could plug in 1. So we have 4. Don't forget to put a space for your x squared. -5. For x, and then -1. So I bring down that 4, and we get 4, 4, 4, -1. Very close, but not going to work. So let's try -1. Bring down the 4. Let me just move my screen up a little bit. So that's going to be -4, add going down, multiply going up, -1, 1, and that's going to work. So this makes a quadratic, 4x squared minus 4x minus 1. And if we're going to find this one, we could use quadratic formula, right, to find the zeros. That's how we could always find zeros. So we could say x equals -b, right, plus or minus 16 minus 4 times 4, well, that'd be 16 again, times -1. So that's over 8. So 4 plus or minus, that's going to be positive 32 over 8. And we can simplify that, but you can already tell right away, well, maybe not right away, but you can tell right here that we're going to have a root 2, so this will not be a rational zero, right? So I'm just going to simplify it, but using the quadratic formula, we can always find all those zeros. So that's going to be, I'll just put 1 plus or minus root 2 over 2, okay? So if we're going to put all the zeros, it would be those 2 and our -1. But when it says what's the rational zero, we only have one, which is -1. Okay, so one rational zero, and then I'll just put zeros all together. We're going to have two irrational zeros. Okay, now let's consider those factors. So you may have seen up here that when we have the root 2, we actually have the conjugates. So I'm going to pull this up here and write this separately, right? So we have, so it's a standard form. We have 1/2 plus root 2 over 2, and 1/2 minus root 2 over 2. So you can tell we have these conjugate pairs. And conjugate pairs also occur when you have imaginary roots. Okay, so if you know that a plus bi is a root, a minus bi, as long as b is not 0, is also a root. Okay, all right, so those are going to be conjugate pairs. And then when we consider factoring, okay, so just a review, you guys are used to factoring to make them irreducible over probably rationals. Okay, so when we consider real zeros, that means that we cannot have the zeros that include imaginary. Okay, so any prime factor would be irreducible over the reals. Okay, so when it says prime factorization, oftentimes we'll leave it with without the imaginary roots. Okay, all right, so let's go to writing some equations. So here we have, we want a 4th degree polynomial, and again, I want to highlight these sorts of problems. There will be multiple answers, and I'll show you how, but we're going to just write one, okay? So we want a 4th degree polynomial with zeros -5 with a multiplicity of 2, and 1 plus root 3i. So if we know that 1 plus root 3i is a root, we know that its conjugate, 1 minus root 3i, is also a root. Okay, so looking at this, I'm going to separate this because this has the 2, so it's going to be x plus 5 squared, right? So that's going to be the multiplicity of 2. And then we know that we're going to have these two factors here. So for these two, I'm going to practice with the sum and product, right? So when we add those together, we get 2. When we multiply, we're going to get the first term, 1 squared, right? Minus 3i squared. So that's just 1 plus 3, which is 4. So when I write this as a polynomial, we know that we can have this as the first term. So I'll put f of x here. So I could write my equation. So this is x plus 5 squared. And then for the second half, it's going to be x squared minus the sum plus the product, which is 4. All right, and then so from here, we can leave it in factored form, or we can multiply it out. Okay, so if we have to multiply it out, we're going to have to distribute everything. Okay, so the quickest way to make sure you can find those equations is to use the sum product. Now, when we say there are multiple answers, you could have a coefficient over here. So an A could be 2 or 3 or -1, and that's why there are multiple answers. Okay, now let's get to the fun stuff. So here we have a polynomial, and we're given one factor. So we want to find all the possible factors. And so this is going to take a little bit of work, so I'm going to use the space up here for this one. So we have the factor x squared minus 6, and we know that that's going to go into this polynomial. So I'm going to use long division, right, because we have a polynomial going into another polynomial. So this is going to be x squared minus 6 is going into x to the 4th minus 2x cubed minus 3x squared plus 12x minus 18. Okay, so For this one, we know that we can multiply this by x squared. So this will be x to the fourth. Remember, there's a 0 here in between, and minus 6x squared. All right, and remember we're subtracting here, so this is going to be negative, let me change colors here, back to purple. This is going to be negative 2x cubed, and then this will be plus 3x squared. And now let me bring down the 12x. So we have, when we look at this one, we know we can multiply this by negative 2x. So negative 2x cubed, nothing in the middle, again, remember, and we have minus, so that's going to be plus 12x. Okay, so both terms go away. All right, now we bring down the 3x squared minus 18. We multiply this by 3. Oop, different color. I'll stick with orange. So that's going to be plus 3, right? So that's going to be 3x squared minus 18, and we get a remainder of 0. Remember, we're supposed to have a remainder of 0 because this was a hint that went in there. Okay, so we have x squared minus 2x plus 3. Okay, so this is, so if we say what's irreducible over rational, so let's factor this out. So I'm going to write it down here. So x squared minus 2x plus 3, right? And we had the x squared minus 6. So remember, for rationals, we only want, terminating decimals, fractions, numbers that are not going to be square roots or anything like that. So if we look at this minus x squared minus 6, we know we're going to get a square root there. Okay, but we can factor this x squared minus 2x plus 3, maybe? No. So we can't factor that one either. Okay, so that's going to be it for f of x. And that's probably where you would have stopped in, when you first started learning how to factor, right? So that's going to be over rationals. Now we're going to factor over reals. Okay, so what I'm going to do over here is I'm going to do a couple things. So first, I'll have the x squared minus 6. So the x squared minus 6, I definitely know I could set that equal to 0, right? That's just going to be 6, and then x will be plus or minus root 6, right? And so that's as simple as it gets, but that's still a real number. It's rational, but it's real. Okay, so over the real, so that's good. And then I would just want to check over here for the x squared. Okay, so for this one, when we have x squared minus 2x plus 3, well, I'm going to put that in the quadratic formula, so x equals 2 plus or minus 4 minus 4 times 3. Oh, you already see the negative there popping out, so that's going to be 2. So that's going to be 2 plus or minus 4 minus 12 over 2. Running out of room, but that's okay. So 2 plus or minus, that's going to be negative 8 2i root 2. Divide by 2. You can see that we're going to have those 2 cancels out. So we're going to use this when we get over to the factor form. Okay, so when we want to factor this over the reals, we can have radicals. These are good, but we cannot have imaginaries. So I'm going to say this is f of x, and we're going to leave the trinomial in place because we cannot factor it without using imaginary roots. And this will be x plus root 6 and x minus root 6. So that's being shown irreducible over the reals. All right, now let's continue on. Let's use what we figured out with this these i's. Okay, so completely factored form. We know if we keep going with that, that would have been 1. So I'm just going to put this over here. So x equals 1 plus or minus I root 2. Okay, so it looks a little confusing, but we know we can rewrite this. So f of x is going to be a little bit long. Is going to be x minus 1 plus root 2, and then x minus 1 minus root 2. And then we have the radicals, x plus root 6, x minus root 6. So that is completely factored form or linear factorization, right? And so here we have, find the zeros. Well, we already found 2 over there, so I'm just going to write those again. We found that x equals 1 plus or minus. I'll write it as root 2i, and I'll make sure to put the I is over here. Okay, and so we have those two, and then the next part is just to make sure we include the radicals, right? So those are from before. So we have the root 6 and then positive and minus, so plus or minus root 6. So we know that this is a quartic, so we'll have 4 roots, all right, or 4 zeros, I should say. But the first 2 are conjugate pair imaginary roots, and the second pair are conjugates of irrationals. Okay, so 4 roots there. And so that was something that we could not use the PQ test, right? We couldn't use the rational roots test because neither of those are rational. All right, so the last problem that we're going to cover is given a function and 1 0, find the other zeros. So you know that you could see right here in this equation that you're only going to have 3 and you're given 1. But they say you're given 1, but you're actually given 2, right? So if you know that -1 minus 3i is a root, then you know -1 plus 3i is a root. And so if you're going to write the equation with these two, well, the sum of those two equals -2, and the product is going to be 1 minus 9i squared, which is 1 plus 9, which equals 10. Okay, so if we're going to write this as a polynomial, it would be x squared plus 2x plus 10. All right, so if we know 2 roots and are given with the imaginary roots, right, those conjugate pairs, well, if we divide this polynomial by that expression, we can find the last root. So I'm going to use some long division. So x cubed plus 4x squared plus 14x plus 20. And this was x squared plus 2x plus 10. So this will be x cubed plus 2x squared plus 10x. Subtract going down, plus 4x, bring down the 20. So it's going plus 2. And so this, just to verify, that's 2x squared plus 4x plus 20, and there's no remainder. So if we're going to find all the zeros, well, we know that in factored form, it would have this x plus 2 and have this root, right? So writing them all together, let's stick with purple here, we know that -2 is a 0, and then we know those 2 zeros that were given up here, -1 plus or minus 3i, finish out to make 3 zeros.